Alright, let's get started for the day. Sorry I'm running a little bit behind, but you know how things go. So let's do a little bit of announcement stuff. So let's make it a big font. Okay, so project 3 is out. It is a Skew heap. So basically, at least the way I look at it, project 1 was okay. Project 2 was absolute terror. And so project 3 is definitely doable. I think it's almost a break, but that doesn't mean you should start late. You should start now. You should get it done. So I actually finished project 3 last night. I wrote it up. So there's a number of little tricks that you might need or want to think about. I'm doing pretty well comparatively. I think overall, just trying to get work done. So all right. So yeah, there's a number of little tricks that I might try to point you to. For project 3. Basically what I'm saying is that, like, in terms of the projects, I think project 3 will be quite a different experience for you. I'm hoping, at least. So, alright, and so what do I want to focus on today? So, the first announcement I really want to do, yep, that's the first announcement. When will the first midterm be out? Hopefully today sometime. My idea for the first midterm, because I think a number of the other teachers have already done this, and I just wanted to wait until the end of project 2 to even release a midterm. I think it's going to be take home. Let's give that a, and it's also going to be collaborative. So I'm going to design something that is built for maybe small groups of between 3 and 4 people. 5 is probably too big, just because if it's a group of 5 people, it's probably too many. So let me talk about the material. Basically everything up to maybe array-based heaps. So let's not include, at least on the first exam, let's well, then you can make some. I was thinking about that just now. I mean, more seriously than perhaps that question. Yeah, I was thinking that we could give people friends. People could I mean, you can always do it by yourself, but yeah, I see. We can. I don't know if you guys would prefer it if I just came up with lists of people that you wanted to. If you want to work with someone, you can request it maybe, but if you don't know anyone in the class because this is all online and maybe you don't actually really know anybody, I could generally come up with like a breakdown of people. Yeah, so when will the midterm be due? I guess that's a decent question. So the due date is probably going to be like maybe next Friday, maybe. This is one thing that I generally do like. About the online teaching format is that I can give exams and have them have a week where you can work on them. So it's not just like you sit down in class and you answer like a 5-minute problem that's really simple. You can answer like a slightly more involved problem. You can actually think about it. You can, throw it around in your brain and that kind of stuff. So I think that maybe that'll be. So once I release it, you'll have 1 week. So it'll be release plus 1 week. And I think maybe on the Discord I will set up breakout rooms for you to work together. All right. Oh yeah, and then maybe I will. I have a bunch of like previous exams that I've given, so maybe I'll release previous exams as a kind of study guide today. And yeah, and then maybe I'll release the exam formally tomorrow. Well, so let's say I'm gonna release the exam tomorrow. Basically, I said that the homework was due, is due today. But if you need an extra day or something, you can always ask me for it. I set the homework due after project. That's really all I cared about. So, I mean, yeah, I'm not gonna. If I release the exam, it's gonna be kind of later tonight. I'll kind of organize you into groups today, I think, and then we'll get everything set up. Okay. So yeah, we have project 3 is out. That's excellent news for everybody. First midterm will be let's just say it'll be out to tomorrow. I might release it today, but let's just say tomorrow, and then yeah. So I think this is a general Okay. Well, yeah, I can kind of explain ternary trees a little bit. So, I don't want to explain them too much because you have to, that's the whole point of that homework problem, is for you to try to understand them as much as you can. But, okay, let's talk about, so let me call this a explanation of ternary search trees. And let me just say that I need to release, I don't know if it's a correction or a slight amendment or a clarification, or we'll call it a clarification. It has to be a ternary search tree. It can't be a tree, or just a tree. And so so if you think about a ternary tree, so basically the term ternary just means 3, right? And so what that generally means is like 3 children, right? And so the purpose of the homework problem is to get you to think about how, let me think if, okay. Let me see if I can pull up the homework. So here is the Here's the question. Nope, that's not the question. Here's the question. So explain the insertion algorithm in a ternary tree with no balancing operations. So let me try to show you a little bit about, like, the hint I gave was the structure of a ternary node. So you notice here that basically there's 2 values and there's 3 pointers. So you know there's 3 pointers, but the real question and the trick here is why are there two values, right? Well, in a binary search tree, you always ask, do I go left or right? You know, so basically if you have a binary search tree, then what you have to do is you have to say to yourself, at any point, now some of these could be null, but basically if I am here, and say this node is the number 17, this node is the number 8, this node is the number 32, then the thing that we know about these nodes is that basically what you have to do is the algorithm, basically every algorithm in a search tree, right, whether it's find or insert or delete or whatever, it all uses the property that when you get to any particular node, and like let's say that we're inserting 12 or finding 12 or whatever, so if you're trying to look for the element 12 and you look at 17, then what you know is that you're going to have to go to the left. And the question is, how did you know, right? How did you know to go left? And the answer is, I mean, at this point you're pretty clear on this. You compare it to the value in the node. Well, that's exactly what you got to figure out. So basically, now for a ternary search tree, you don't have 3, or you don't have 2 children, but you have 3 children. So how do you manage that? Like, what do you do for that? So here we are. Here we have 3 children. And then, let's see here. There we go. And so here's my hint. Let me see if I can do a good division of this thing in half. So remember that each one of these nodes, I should have actually done this before, each one of these nodes has 2 children, or has 2 values in it, or at least 2 spaces for values. Sometimes they may not be occupied. So you kind of got to draw it like this a little bit. So if the value is equal to the parent, it goes to the... No, not. I wouldn't do equal. So here's the thing. Let's say that we have 2 values. Let's say we have the values, but you're almost there. Yeah, I mean it's not quite right, but you're like getting there. So let's say that this is 14, and then on the other side we'll put 72. Okay, so let's say that those are the 2 values in our ternary node right here. And now let's say that I try to insert, I don't know, and of course you don't know what the algorithm is, but let's say that I try to insert 7, right? Well, the old binary search tree algorithm says, well, 7 is less than 14, so we're going to stick it over here. And then you're like, okay, let's insert, I don't know, what's another number to insert? Let's say we insert 35. And you say, or let's not do 35. 35 is the trick case. Let's say we do 108, right? So now you insert 108 over here, just like a binary search tree. And now let's do the number 35. And then you say to yourself, well, 35 isn't less than 14. And it isn't bigger, and it isn't bigger than 72. It's kind of in the middle. Oh, hey, we have a middle node. Can we put it here? And then the question is, if we do this, can you always find it, right? Do you always find the node if you insert it here? So basically, if I say, okay, now we have 14 and 72 up here. If I come in looking for, say, if I come in looking for, I don't know, let's say 28, then would you be able to insert it? So, and here's actually an edge case, right? So let's say that we wanted to insert it. So we're like, okay, we'll insert it in the middle node and put it here. And you see that this is actually, it's not totally wrong, but it is a little bit wrong, because then this value is bigger than this value, and this value is to the left. So there's a few edge cases that you have to deal with. Like maybe you decide to flip these two values, or maybe you just decide that, like, this kind of thing. Yeah, I mean, you can use letters, you can use words, you can basically do a whole bunch of stuff. Like, using numbers is kind of helpful because it does show exactly what's going on. So basically, I don't want to say any more, because that's basically it. The whole problem is an analogy. It's like, in binary, we do X. So in ternary, we do something like X, right? Well, we could always make a visualization, right? So there's basically just a few edge cases you have to deal with. What I suggest is that you, did you understand what I was doing here, right? Like, did you understand the process that I was just going through? Because I think I've kind of explained it, right? I think you should just kind of, like, yeah, I don't think I can say too much more without just completely giving everything away. So, all right. Cool. Anyway, I mean, yeah, I did. Maybe I did too much. Oh well. So, alright. Yes. Yes. So let's get over, yeah, so my hint is just kind of keep inserting nodes until your algorithm works, right? Just make sure that you can kind of keep inserting nodes. And, yeah, I'm not asking for, like, a deletion method or any of that stuff. I'm just asking for a, whatever I'm asking for. So, okay. I think last time I did an implementation of an array-based heap, or I'm sorry, a leftist heap. Of course, I caught this after the lecture. I couldn't fix the problems with my code. I couldn't figure out what was going wrong. This was wrong. This was p current. Remember how it was outputting like a duplicate side of the tree, and quote unquote we couldn't figure it out, which really means I had no idea what was happening. But what was really happening is this was wrong. So it was outputting the same side of the tree. It was pcurrent.left. So it was actually, I think let's run this thing and see what happens. Wow, look at that. look at that. Kind of looks right to me. I mean, maybe this is extra. I think when I implemented, well, I guess since you have to deal with null path lengths, you know. Okay, so all right, so let's run this thing and see what it does, because I'm kind of interested. Let's see if it works now. So let's insert 17. Cool. Let's insert 5, and I guess we have to remember, I think this is a max heap, because it seems to be saying if left tree value is bigger than right tree value, then we merge on the left tree. So I think that's a, I think that's going to be a leftist, I think it's going to be a max heap. So you can also build a min heap, and incidentally, your project is not a max heap, your project is a min heap. So here, what do you see, right? What you see is that it inserted 5. Remember, it always inserts on the right, right? It did a pu tree.right is equal to the merge process. But then down here, what it did is it recalculated the null path lengths, and because, basically, let's go through the rules again. So for a leftist heap, here's 17. Oops, that's too big. I think that's too much. Nope, that's going to be invisible. Okay. 17. And then let's do another node. Let's say, so remember what you do. What you do is all things in the universe are merge in leftist heaps and skew heaps, right? So in a leftist heap, for instance, when you want to merge, what you do is you take these two nodes and you say, okay, who's the bigger node? And the bigger node is 17. So then what you do is, so basically this is merging these two. And so the next step is to merge the right child of 17, which is actually null pointer, with 5. And so when you merge a null pointer with 5, you stick it on here, right? Because if you're merging a null tree with something, you do this, and then remember you have to calculate the null path lengths, right? And so what is a null path length? Is the shortest path to a null pointer. So hopefully the exclamation marks indicate to you that it's not the height of the node, right? You have to be careful about that. So it is, not the height of the node. So let's think about null path lengths here. So the null path length is what? In this case, it is so here the null path length is, I guess, 0, because it has a null pointer on it. The null path length here is 0. So, and I guess the null path length of this child here is -1. Remember, because it's a null pointer. So what you need to do is you always need to make sure that all the null path lengths are bigger to the left. So that's why we do the swap. So you do the swap because there's a null pointer here, and there's a null path length 0 node here, so we push this over to the left, and then we rejoin, like this. And then here's the -1 sitting on the right. All right, and so now let's insert another node. Let's insert 20. So remember, if we insert 20, it's going to become the new heap top, the max of the heap. So we see that what happened is when we merged it, let's actually do it here. So when you merge these two things, what do? Right, so the thing is that you're going to merge, basically you're going to merge the biggest one, and then on the right you merge the other heap. So basically the first stage of the merging process is this, where it takes 17 and it makes it the right child of 20, and then we see that we have the same problem as we had before. 20 has a null path length, or I shouldn't say 20 has. The null path length on the right side is 0. Why is it always left and not right? What do you mean by that? Help me out. What do you mean by that? Tell me more. Anyway, so then the point is that the null path length on the left is smaller than the right, so then we swap it. And I guess we gotta redraw the line. Oh, I mean, so you could make a rightist heap where everything was completely symmetric. Honestly, I'm not sure. So I'll say this: there's no algorithmic or like actual reason to pick left over right, but they're called leftist heaps. So left. We could invent a rightist heap, which is exactly the same as a leftist heap, except everything is just mirror symmetry flipped. And all the properties would be the same. Everything would be the same. So you might be asking, like, why do we care so much about this type of heap? And so the answer is that this type of heap has a property. So skew heaps and leftist heaps, as well as binomial heaps and Fibonacci heaps. So those 4 types of heaps, so binomial, Fibonacci, leftist, and skew heaps, all have a property, which is that they are mergeable in log n or less time. And so if you think about what it would mean to merge an array heap, you would actually have to basically insert all elements from, if you have 2 heaps and you're going to merge them, then you have to insert all the elements from one heap into another heap if you do it by arrays. So if you use arrays, then you have to insert each element from heap 2 into heap 1. But why are skew heaps and leftist heaps mergeable? So let me show you an example. Let's make a skew. Let's make a leftist heap and make 2 leftist heaps. So, and then let's talk about the merge algorithm. Let's say. All right, so let's make this 12. Let's make this 5, 8, 3, 1, 2, 1. Okay, so that's one heap. And now let's do the other heap. And so let's look at the other heap. And so the other heap is going to be something. Let's make it a different structure. let's say that this is, I guess I'll delete all the numbers so that we get a new thing. Let's say that this is 11, whoa, what happened? Oh, wow, that really sucks, it just crashed. Inkscape is not 100% stable. All right. I think we got to redraw. Let's make this, save it so that if it crashes, I can just reload it real quick. So let's make this leftist heap have a little bit of a weird property. Actually, I think I intended this to be this child here, so I don't think it matters, but I'll do that because that's what I wanted to do. Okay. So now let's say that we're going to merge these two heaps, and let's just go through the process. And hopefully this doesn't crash on me this time. And you notice that this, you might be a little confused because this is actually, quote-unquote, taller on this side than it is on this side. But this is actually a leftist heap, and you'll have to think about it in terms of null pointers, null path length. Because if you look at it here, the null path length of this node here, I guess it's the minimal path. So here you have a null path length of basically 0 because you have to go through this node. Here you have a null path length of -1, -1, -1, -1. So it's always, so this is a leftist heap here, and then this is a leftist heap, and then here the null path length is here the null path length is actually 1, and here the null path length is 0. Okay, so let's put in some values. Okay, I really wish it wouldn't default to a crappy size. Okay, let's make it 16. So let's make this 10. Let's make this 5, 3, 7. Let's make this 13, 10, 8, 2, 5, 7. I guess I have to come up with something in between. 11, 4, 1. Okay. All right, so let's merge these two things. So remember how you have to merge. You always have to merge the largest node becomes the new subroot. And so in this case, we're looking for the actual root. So what we're going to do is we're going to merge this guy, right? Because this guy has 13 and this guy only has 12. So this one's going to be the root. And then what we're going to do is we're going to delete this edge, and we're going to merge these two things together. So now, the right edge here is going to be the merge of, so now we have to merge these two things, okay? And then you say, oh, I see. What I do is I say, well, now this has to be the new subroot, right? Because 12 is bigger than, what you call it, 11. So now, let's go to the next step. The next step is that we merge 12 on as the right child, and then you have to merge these two nodes. So you pluck off this stuff and you say, okay, so this becomes the right child, which I'm going to draw over here because I need some space. And so over here, then we're going to say now the right child of the right child is equal to the merge of these last two things here. And then you say, okay, well, 11 is bigger than 10. So how do we merge those? So we merge, remember that what we do is we merge this on the left, we merge this into the node, and then finally we merge this last one, and so the point is that this is basically being merged with null pointer. And so at that point you say, okay, now what I can do is I can take this whole heap and I can just basically, now that I see a null pointer, I can just stick this on here, because this one didn't have a right child to begin with. Okay. So that is half of the merge process. So now the question is, how do we do the rest? And so the answer is that what we need to do here is that, so what we need to do is compute null path lengths, right? So this merging process happened on the way down, and so now on the way back up, we have to look at null path lengths. And so this is just for leftist heap. So for a skew heap, so let's actually do this for both leftist and skew, and we can use the same starting example. So let's do leftist first, and then we'll do skew. So here, we said that the null path length here is, I guess you can define it, is it defined as the minimum plus 1? Is it defined as the minimum? Now I'm forgetting, so, I mean, I guess we can make up a definition. The path length of a given node to its nearest descendant null node. So or we could look at the visualization. Okay, so the null path length here, let's go through all the zeros. Here's a 0, 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 0, 0, 0, 0, 0. Okay, now finally 1, 1, 1, and 2. And I guess technically this one, the null path length on this one is 1, it's the minimum of the 2. But the point is, it doesn't actually matter what the null path length is at the root. It only matters, it's just like AVL trees, it only matters what the heights are at the children. So basically, actually, this is almost done, right? There's almost nothing left to do here. The only thing left to do is to basically say, okay, 0's on the left, 0's on the left. This is these are equal, so you have to leave them. There's no reason to swap. This is fine, right? Because the null path length here is 1 and 1, so that's okay. The only violation is right at the root, where we look down and we say, the null path length going down on the left side is 1, and the null path length going down on the right side is 2. So for a leftist heap, here's what we do. We will swap this with this. So you basically, when you find the imbalance, or I guess when you find the right heaviness, or the whatever you want to call it, you'll swap the two trees, and that's all you have to do here. Let me try to kind of redraw this line. Yes. So actually, this is an example where leftist heaps do less work than a skew heap. So this is what the leftist heap does. It just flips these two subtrees. Now let's talk about what happens in a skew heap. So basically a skew heap ends up with the same thing, except we don't care, we don't have any of these null path lengths, which you're like, wow, wait, we don't have this extra complicated feature in our project. The answer is no, you don't. No null path lengths. You just have to remember what the insertion path was. So the insertion path was here. Let me mark it in green. So this was the insertion path. And so the point about a leftist heap is actually what you have to do is you always swap. So if it was along the insertion path, so you would swap the children here, but there's no children. So the first thing you do in a skew heap is you swap this subtree, you stick this over here, and you take this one and put it on the other side. So you just always swap. And then you're like, wait a second, but that becomes, unbalanced on the other side, blah, blah, blah. Well, the point is that a skew heap doesn't care, right? It doesn't know. It's basically just, it's not random, it's really just alternating left and right. And so here, let's say that we group these now, and let's say that we group these now. So then what you'd have to do is, remember this is along the insertion path, so now you flip left and right. And so here you go. I guess I have to redraw this green, or maybe I can just drag it. There we go. And then finally, here's another one. Here's another one. You just flip them. And you might be thinking to yourself, like, this kind of looks like a leftist heap, But the rules are completely, well, not completely different. Literally, I guess the only difference in the real rules, right? The only difference in the rules is that you don't check null path lengths because there aren't any. You just immediately flip, right? So the other merge, so the reason why you need the merge operation, and you notice that the merge operation basically is O of the height, right, of this tree structure, right, which is actually which has heap structure too. And so amortized, at least overall, the runtime of merge for skew and leftist are O of log n, where n is the number of elements. Basically, n is the you can consider n to be the like basically the sum of like n1 plus n2, where n1 is the size of the first heap and n2 is the size of the second heap. So, but basically you just pretend like you can even take the max, or you can just say n is equal to the max of n1, n2, etc. In big O sense, it doesn't actually matter. Okay. So all right, and then what else should I say about this? So I guess I've done one example of merge. If we pull up the visualization, we can actually see a bunch of other examples of merge. So if I pull up leftist heap, or let's pull up skew heap and just do it this way. Skew heap visualization. So the way that we get to see let's insert a bunch of nodes. Um, 18, and this is actually a min heap, so yep, and then 25, 35, 72, 51, 128, 288, I don't know, 315. And so you see that all this swapping back and forth does actually create a relatively balanced tree in general. Let's say 2. Of course, now that's messed up, so let's say 3, 4, 16, 17, 23. Okay, so now that's looking more like a skew heap, something kind of random like that. That's good. Okay. So if you want an example of merge, the way to think about it is that the way to merge things, remember what the deletion algorithm is, right? So if you delete something from a skew heap or a leftist heap, the algorithm is that the new root is now equal to basically the merge of the root.left and the root.right. And then what you have to do is you have to like return the root.element. And of course this is like pseudocode here, because at some point you probably have to set like root.element equals some kind of temp, because then you're eventually going to delete the root. And then you return the temp value. Right, so that's kind of the algorithm for, well, this is the algorithm for both leftist and skew heaps, right? Because the only thing that differs is that either this is merge leftist or it's merge skew. And so that's the point here. Okay, so let's remove the smallest element and slow the animation speed down quite a bit so that we can watch it merge. So let's remove it. Okay, 2 is going away. And now we have to merge these two elements. So here you see that they're going to merge 4 with 3, and so 3 is going to be the new... What they're doing here is they're saying 3 is going to be the new top, because that's the minimum. 4 and 16 now have to get merged. So let's see what happens. So 4 and 16 have to get merged. And so now 4 is the top, or of that subtree, so it'll go 3, and then 4 will go in here. 17 and 16, so 16 is going to be the new top. So when it detaches, it's going to send 16 over here. And then 17 is going to go in on the right side. And then, yep, so we're going to put 17 in on the right side. And then remember that this is a skew heap. So merge says to always swap. Swap. So then you stick in 16 over here on the 4, and then you swap, and then you stick 4 down there, and you swap. And that's it. So if we remove the smallest element again, this is almost like insertion, actually, because we're merging with a single element. So, for instance here, you merge this on the right side, so 4 is smaller than this, so we just merge it to the right. It's smaller than 5, so we merge it to the right. And then here, you see, it's bigger, it's smaller than 25. So, yes? Do you have an opinion? Okay. You know, I should play the Stop the Hammering video. Okay. So, anyway, so basically 25 goes in as the right child of 23, and since 23 doesn't have any children, we can stop merging. So here we go and we merge, and then we swap, and then we merge. And I think then we swap, and then we merge, and then we swap. Okay. So my question is this making any sense? Right? Does this vaguely make some... Does this make any sense? Alright, let's do remove smallest one more time. Sure. So removes 4. And so what it's going to do, it's merging 5 and 16. So it's going to take 5, and it's going to clip off the right child. And so now it's going to merge 12 and 16. So now we're going to merge on the right because 15 is smaller than 16. So now we're going to pluck off 35 and merge that to the right. So now 35 is going to come down to the right. Swap. 16 is going to come down to the right. Swap. 12 is going to come down. I'm sorry, so 15 is going to come down. Swap. 12 is going to come down. And swap. And so you see that the advantage here is that basically you have a 50-50 chance at any point of inserting into the heavier side, right? So basically as you insert nodes, you're going to have a higher chance, or you'll have a half chance of inserting on either side of the tree. And so that's kind of a good thing, because if you have a 50-50 chance of inserting on both sides of the tree, then overall you should expect, on average, I mean, there's ways to create really bad skew heaps, but, you know, on average you should expect that it will produce a decently balanced thing. So you see that here 12 is smaller, so we merge to the right. 15 is smaller, so we merge to the right. 23 gets plucked onto there and swapped. 12 gets 15 as a right child, and, well, they both have 15, so they both get swapped. So that's basically it. What was I going to say? Oh, right. So for the project, there's a little detail, at least to get the sample output that the course chair got. I don't know if this is saying too much or whatever, but there's a decision you have to make, and actually that we're about to face that decision right now. And the question is, what happens if you remove the smallest and then look at these two elements here? They're both 15, right? So who goes onto the who goes onto which side. And so when you merge these two, actually you don't really know, right? You could theoretically make this 15 a right child of this 15, or you could make this 15 a right child of this 15. I think generally what this algorithm does, and if I'm not mistaken, it'll make the one on the right a child of the one on the left. So basically when you write your merge algorithm, you're going to have a left one and you're going to have a right one. Let's check and see what this one does. Yep, so you see here what it did was it made this 15 the parent and this 15 the child. And now you think to yourself, well, how do I know which one it should make the parent and which one the child? The answer is that there's not, it doesn't actually matter, but you do have to pick one. So they just picked the left one here. And so here we go. We'll merge this with the 288. And then the 288 will come down and become the right child here. Okay, so, and then we stick it, well, first we have to swap. Stick it onto 15. Swap. Stick that onto the parent 15. And one last swap. So you see that overall, like, this kind of skew heap structure kind of maintains balance because of the way that the skew heap works in terms of the merge process. Okay. So, all right. So, yeah, that's the one, that's the little current hint, that's the first, like, hint 1. In order to match the output, you have to play with the order if the two nodes have equal priority. Okay, and let me actually check. I think that if let me see here. So, nope, that's not it. Here it is. Okay. Yeah, so if the patient's left priority is less, then you'll merge, let's see here. So if they're equal, then you take, yes, so if it's equal, crap, I was typing my actual code. So if the two priorities are equal, you want to take the right to be the new root. So actually, the way that this one works, so this is opposite of the visualization. Okay, so that's one of the hints that I'm going to give for this project, is that if the two priorities are equal, you actually have to take the right one, not the left one, as the new root. So you notice that in this one we took the left 15 became the new root. Like if we skip back and we remove the smallest element and then we step forward, the important step here is like what happens when you compare the equal ones, and you see how it took this way. So your project needs to do the other way. Okay. So I'm going to spend the last 10 minutes, I think I've done enough on skew heaps for now. We've talked about the merge process a bunch. All I'm gonna say, I know it is harder, but the only thing I have to say about that is that, like, I did it like the Viz way, and wasn't getting the same results. So when I flipped it, like when I literally removed I had this operator, and when I changed it to this operator, that fixed it. Then it matched completely. Like, the thing that I was creating was a skew heap, right? Because, as I say, there's a choice that you have to make when you're implementing the skew heap. Do you put the equal sign on the one thing, or do you put the equal sign on the other thing? And it's so finicky and so nuanced that's why I'm mentioning it here. Okay, so let's talk about So I'm not sure how much I'm going to talk about so far, but I'm going to talk about, my goal here is now to introduce binomial heaps. And so I think binomial heaps are a kind of fun application of heaps. I'm not sure that they're really the most practical objects, but certainly Fibonacci heaps are not always the most practical objects, but these objects are they have such a beautiful structure that I think it's important to talk about them. So before I introduce a binomial heap, I want to introduce what I'll call B sub n. So maybe I'll do that in so we need to talk about B sub n's. And so what are B sub n's? They are trees of a certain structure. And so let me show you the structure. This is what we call B0. Okay? And assume that these are subscripts. I might, whatever. So this is B0. Hello, B0. This is B1. B1 is basically two copies of B0 like this. So here's a B0 and here's a B0. Let's name this. Okay, so that's B0, or I should say that's B1. So now your question should be, well, what's a B2? I'll show you in just a second. So a B2 is two B1s. So let me show you how to make a B2. Let me delete this and delete that. So you take this, and then the general way that they tend to draw it is that they'll just put, maybe we'll move this over a little bit. They tend to do this to draw it. And so what you do is you take a So you see that this is a B1 here, right? This is the top of a B1 right here. And this is the top of a B1 right here. And you've joined them like this to make a B2. Okay, and then you ask, well, how do I make a B3? So what you do is you take two B2s, one becomes the top one, and one becomes basically the rightmost child, like this. So this is a B2 here, and this is a B2 here. And this is what is called a B3. Well, nothing in particular. I'm just defining all of these terms, right? Like if you don't understand there are 3 children. Yes. So a B1 has 1 child, a B2 has 2 children, the root of a B3 has 3 children. If we look at a B4, and this might be where we stop, it might get kind of big, maybe we'll do a B4 and a B5. So here is a B4. Well, well, so basically you would use all of this in a binomial heap, okay? So these things become a binomial heap, all right? And so that's the trick to it. So this thing here is a B4 structure. And so let's do it. There we go. So you see how to make it, right? And so what are the things that you need for a binomial tree? Basically, each node needs to have a vector, maybe, or some kind of array, probably a vector, of children. Because the thing is that you might end up making a B1 out of a B2 out of a B1, or you're going to be messing with these, and so that's kind of the idea here. And you notice and the reason why the structure overall is going to be called a binomial tree is that you notice that if you do, I guess I should just do it like this maybe. Let's see if this renders correctly. It sometimes renders correctly, and sometimes it explodes. Yes, it did. So 0 choose 0 is 1, and then 1 choose 0 is 1. And so if we look at a B1, we notice that on the first level we have 1 choose 0 nodes, and in the middle level we have 1 choose 1 nodes, which is, it's not very surprising because 1 choose 0 and 1 choose 1 are both 1. So that's not very entertaining. But let's look at a B2. The B2 has 2 choose 0 nodes, right? As the first thing, because 2 choose 0 is 1. And then it has 2 choose 1 nodes. On the second level. I'm sorry, 2 choose 1 is 2, so I need to fix that. Which one is right, which one is wrong? That one. Okay. and then 2 choose 2 is 1 again. So, and then you might notice here, this is 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3, because 3 choose 0 is 1, 3, 3, 1. Then you get 1, 4, 6, 4, 1. Basically, the number of nodes at any height is the type of tree you have. So if this is a B4, choose the level that you're at. So for instance here, if you do the second level, you would say 4 choose 2, and 4 choose 2, remember 4 choose 2 is equal to 4 factorial over 2 factorial 4 minus 2 factorial, which is equal to 4 times 3 times 2 times 1 divided by 2 times 1 times 2 times 1. And so that is equal, when you simplify, to some stuff. So let's write it down first. Okay, didn't like that. So the point is that here, you know, the 2 and the 2 cancel out with a 4, and so the number you're left with in the end is just the number 6. And so there are 6 nodes in this level. So that's pretty interesting. Okay. So at this point, you don't really know what a binomial heap is, right? At this point, the only thing that you actually know about are these BNs, right? And the BNs aren't exactly a binomial heap. They are parts of a binomial heap, but they are not themselves. Well, I guess they are binomial heaps, but they're like a special case. A binomial heap is actually a forest of trees. So, so a binomial heap, and I'll leave you guys with this. A binomial heap is a forest of trees which contains at most one BN for any n. Up to, you know, up to some finite maximum, of course. Unless you want to consider, I guess, infinite binomial heaps or something like that. So the point is that a binomial heap is basically a vector where at the 0 position in the vector you can either have a b0 or a null pointer. At the first position in the vector you can either have a b1 or a null pointer. At the second position in the vector you can either have a b2 or a null pointer, etc. So basically you have, and at the fourth position of the vector, b4 or null pointer. And so the way that we actually do insertion, deletion, merging, all that stuff, so there is no particular n, right? N is some number like 22,841, right? It doesn't, you know. So the merging process for binomial heaps mimics binary addition, which is pretty cool. Because remember, if you're adding two numbers in binary, let's say that we add 5 to, let's say we're adding 5 to 6. So if we do this, then what we're going to get is, remember, you do binary addition like regular addition. So this is going to be 1, this is going to be 1, and then this one is going to be, so 1 plus 1 is 0, and then you have to carry a 1. And so this basically tells you exactly how binomial heaps are going to merge. Because if you have a binomial heap, this one would be, like the first one would be, this first one would be something that has a B2 and it has a B0. The second one has a B2 and a B1, And when you merge them together, you're going to get a B3, a B1, and a B0. So, so that's how the merging process works. It's basically binary addition. And so I think that's probably all for today. No. I don't, okay, I guess I'll say it this way. What do you mean by n? Oh, I mean, basically all that you know at this point, so don't worry about all this stuff. Literally all you know at this point is if I say B4, it is this structure. It's two B3s where you have a B3 and then the last child of the B3 is another B3. Right? So that's what you have to know. You do not have to, so you don't know what Bn is going to be because you don't know how many nodes you have in the tree, right? So you can't know what Bn is until you do some of the work, right? N just has to do with the number of nodes you have. Yeah, so don't, I will explain more about binomial heaps and maybe Fibonacci heaps next time. This is all I want you to understand for now, is just that binomial heaps use these, basically, this is the way to think about it. The BNs are the building blocks of the binomial heap. And so all I've taught you right now is building blocks. I haven't taught you what the actual binomial heap is. So we still have to do that. But I just wanted to get the building blocks done because we had an extra 10 minutes at the end of this class. So I did it. Okay. All right, so I'll end lecture now. So yeah, I'll be around for a little bit after class. But I got to do some other stuff too today. So anyway, okay, I think that's it for the day. Taught some building blocks, and that's good enough for me.